here. Okay. Okay, very good. Welcome to our session. Today, we are very glad to have Susu Zhang join us to share her experience in processing data. Yeah, that reminds me, a couple of years ago, well, we were thinking about how to use eye tracker to trace the students' thinking pattern, like math ability studies. And now I think, her experience should be valuable. And now let's welcome Susu Zhang's presentation.
Well, thank you so much, Dr. Zhang, for inviting me and for the nice introduction. I feel deeply honored to be able to present here today and share some of our findings from a project that explores the NAEP math achievement gap by gaining insights from test-taking process data. I hope my volume is okay. You can hear me from the back. Okay. Right. So the NAEP stands for the National Assessment of Educational Progress. And this is a continuing large-scale assessment of what US students know and can do in various subjects. Administered about every 2 years, it serves several goals. The first is to monitor changes in US student achievement. It measures the achievement of different demographic backgrounds, and it tries to ultimately guide education policymaking and resource allocation. Federal law mandates that all of the states that receive Title I funds, they need to participate in NAEP reading and mathematics assessments for their students at 4th and 8th grades. The NAEP results are commonly reported as the proportion of students performing at or above 3 NAEP predefined achievement levels, known as basic, proficient, and advanced. An example of this is the screenshot below of part of the definition of 8th grade mathematics basic level. You can see that the students are assumed to be able to do specific tasks at this level, such as simplifying expressions involving integers, using operations to solve real-world problems involving integers or fractions, or something related to geometry, like working on problems related to length, area, and volume. And NAEP encourages the students with disabilities to participate in this assessment as well, if they can participate with accommodations allowed by NAEP. Schools are encouraged to have students with disabilities participate whenever this is possible. NAEP's definition of a student with disability includes students with either an IEP, which stands for Individualized Education Plan, for reasons other than being gifted or talented, as well as some students with Section 504 plan and any other students who have received a accommodation from NAEP, excluding those English language learners. To get an idea into the composition of students with disabilities, we'll look at the distribution of the most common categories. Try to this over here. We can see that out of the students with disabilities, some of the most common categories in those with specific learning disabilities and those with speech language impairments. And later on, we have some smaller categories: autism, developmental delay, hearing impairment, etc. Over the years, NAEP results have revealed that there is a long-standing math achievement gap between the students with disabilities and their typically developing peers. This might sound very reasonable, given that a large proportion of those students with disabilities are those with learning disabilities. However, we should know that this is the case despite that the IEP tries to provide specialized instruction and support to help those students progress in the curriculum, and at the same time, assessment, the NAEP, tried to introduce a sort of universal design tools and accommodation features to improve the test's accessibility and equity. But despite all of these efforts, we have seen that over the years, starting from 2013 to on the next page, some of the more recent years, the proportion of students who are identified at below basic level on NAEP 8th grade math for students with disabilities is much larger than their typically developing peers. And at the same time, that proportion below basic seems to be growing over the years. And in 2022, which is the most recent results, we can see that 78% of those students identified as having disabilities scored below basic in NAEP 8th grade mathematics. Our talk today is related to NAEP process data. I want to introduce a little bit of what this is. Starting from 2017, the NAEP math assessment transitioned for the first time from paper and pencil-based assessment into a digital assessment that was administered on a Surface tablet with a stilo, and this was known as the NAEP. Here's a screenshot of one question out of a math block on the NAEP. You can see that the question itself still looks like paper and pencil-based math questions, but there are some additional computer-based features over here. Student can navigate between different questions by clicking on the question pages. They can eliminate certain choices, use tools such as text-to-speech, zooming, as well as scratch work, and they can click things like clear answer. A byproduct of the NAEP is the streamlined collection of test-taking process data. Here we define process data as the computer log sequence of time span events that documents the actions performed by an examinee in pursuit of solving the tasks. I took a screenshot of an example raw data structure for process data. First column is student ID, second is essentially item ID. And then later on, if you look at the last column is the coding, and the column before that is the associated timestamp. And you can see that each of them is essentially one computer recorded event that documented at this particular time. This is what happened for this student on the interface. Examples of actions on the NAEP includes keystrokes for constructive responses, the students' answer choices, their change in their answers, and eliminations on a multiple choice question, their usage of tools such as scratch work, draw and erasing, text-to-speech, which is highlighting some text and ask the computer to read it out for them, zooming and highlighting, which can show like how they use these tools to facilitate their problem solving. Right? Another example is visits and revisits to a question, which are indicated by enter item and exit item. So whenever we see enter item, we know the student entered the question page, and when we see exit item, we know that they left for something else. The utility of process data has been documented in a lot of existing literature. It might contain a lot of additional information that are unavailable from the final scores of the questions, which is simply what score does the student get out of, say, 1 point or 2 points. Right? For example, there is a lot of literature that documents the utility of action sequence data in understanding subgroup differences. On exams such as the PISA, they've seen that there are gender differences and differences in like immigration status in how students explore some of the test-taking platforms. And there is also literature on differences in sequential patterns observed for incorrect and correct problem solvers. It has commonly been observed that for correct problem solvers, the sequences are more homogeneous, but for those who got the questions wrong, there are a lot of heterogeneity and all sorts of possible ways that you can do something wrong. The NAEP math scores or the performance levels we saw earlier has indicated that students with disabilities are less likely to score above basic. Right? But that's a summative result that simply tells us that they can still improve further and maybe do better in mathematics. Right? Our question here is, can we use process data to maybe a little bit understand how this happened? And maybe it can help us gain some insights into what can we do about it. Right? If we're to help them improve, what are the things we can probably target? And if there are issues with the task design and the equity of the interface, can we try to make the interface more fit? Example questions we might be able to answer are students with disabilities navigating the NAEP interface and tools the same way as their peers, which has consequences for test design and equity. Right? We want to make sure that whenever we have a new platform for taking the test, all the students are using it and benefiting from it the same way. We might also be interested in the effect of specific test accommodations, such as extended time, and how that changes the behavior and outcome of some students. This also has consequences for test design and equity. Right? Another type of question we can try to answer is, do students with disabilities feature specific types of wrong responses, which can help us understand, are there math skills and misconceptions we might be able to target when we try to help students with disabilities improve. So since 2020, the IES, the Institute of Educational Sciences, which is the statistics, research, and evaluation arm of the US Department of Education, launched several efforts to leverage process data to help understand math test-taking behavior for students with with disabilities. These efforts include releasing the restricted use process data from select digital NAEP math assessments to be able to be analyzed by researchers, as well as funding several exploration grants to study how testing behaviors affected math performance in students with disabilities. And the ultimate goal for them is to improve educational outcomes for these students with special needs through evidence-guided research. So in the past 2 years, I was very fortunate to be able to work on a few projects that involve using the NAEP grade 8 math process data from one 15-item block. So it was actually the block I showed in the screenshot earlier, to try to understand math problem-solving behavior for students from various underrepresented groups. For the sake of time, I will focus on students with specific learning disabilities today, which is indicated by LD. And although we did the analysis on some of the other groups as well. And I want to discuss a few recent and ongoing projects that either involve the effect of extended time accommodation or the exploratory mediation analysis. And throughout the survey of these projects, my hope is to illustrate to educators and policymakers how we might use process data from large-scale assessments to answer some existing educational questions we're interested in. And for a lot of the psychometrics and methodological researchers, I hope to illustrate some potential measurement problems and opportunities that are brought forward by the additional behavioral data from computerized tests. All right, so from here, I'll move on to study 1, which relates to extended time accommodation for students with learning disabilities. So NAEP, in order to improve the equity and accessibility of the test, they provide a set of universal design elements and accommodations. Universal design elements are defined as elements that are built into the test interface and are available to all of the test takers. So this can include things like zooming, text-to-speech, except on reading questions, because they're supposed to read it themselves on reading questions, as well as things like elimination, scratch work, adjusting the volume or the size or the color contrast on the testing interface. So all of the students taking the test can use this universal design. Accommodations, on the other side, are things that are provided to a subgroup of students. So if a student's IEP demanded that a specific accommodation must be provided, then NAEP tried to honor that accommodation whenever possible. So for example, if the student's IEP says that whenever taking the test, the student needs extra time, then the NAEP provided extended time accommodation to the student. And there are some other kinds of accommodations as well. So the goal of a lot of the test accommodations, which are provided to some students but not others, is to increase the reliability, validity, and fairness of the scores by reducing the influence of construct-irrelevant measurement errors. If we take the example of NAEP extended time accommodation, here is probably my understanding of their objectives. Right? So NAEP's goal is to assess what students know and can do in mathematics. The standard version of the NAEP 15-item block has a time limit of 30 minutes. However, students with learning disability and English learners might be more impacted by test speediness. For example, they might have higher anxiety level, more likely to run out of time and engage in like rapid response or guessing and missingness due to running out of time. And ETA, in this case, to these learners aim to help overcome the construct irrelevant nuisance, which is all these things that are introduced by lack of time, when speed is not an intended component of the test construct. So let's say we only care about what the students can do and know in mathematics, and we don't care about how fast they solve the questions. Then in this case, it might be reasonable to give certain students who need ETA the ETA. So for the NAEP, students with the ETA accommodation receive 90 minutes instead of 30 for one test block. So as instructors ourselves, we might have seen a spike of ETA requests in our classes in the last few years. And this issue in NAEP and beyond has generated many debates on whether extended time accommodation indeed levels the playing field. There are two main considerations in this problem. The first is the effectiveness. of ETA, which is do students who actually need the extra time benefit from it? And the second one is related to validity and fairness, which is does ETA improve the performance for those learners who need it, but not affect the learners who don't need it? Our project, so this current study, mainly focuses on the effectiveness aspect, not the validity part, which we look at how does ETA affect the behavior and outcome for students with LD, learning disabilities. I feel really fortunate to be able to analyze this data set for two reasons. The first is that NAEP is a large-scale assessment, and it provides a very, very rare opportunity for me to investigate the special group of LD students, which is usually, if you restrict to a school district, is very small population, right? But for NAEP, because they do national survey, I was able to analyze the data with a large enough sample size. And the second reason is the NAEP documented the process data, which can capture the students' interactivity with each of the test questions, which is something I speculate to depend on time credit. So here's a description of the data for this study. Our sample included a total of over 1,500 students with learning disabilities who took this 15-item block in the NAEP 2017 8th grade math. So out of these students with learning disabilities, we can divide them into three groups. The first group are the students who were not granted the extended time accommodation. So this is the red group over here, about 39%. We indicate those by NG. These are students with learning disabilities who did not receive the extra time because that was not part of their accommodations or IEP. They took the 30-minute version. And then there are a remaining 61% of students who were granted the extra time. So they took the 90-minute version of the test. However, it turns out that 45% of the students did not use the extra time, meaning that although they received the 90-minute version, they actually used 30 minutes. And we indicate these individuals by not used. So that's the orange group, NU. The remainder are the students who were granted extra time and actually utilized more than 30 minutes. So that's the blue group, about 16% of the sample, and we indicate that by granted and used, U. The 15 items contain both multiple choice, constructive response, and drag and drop questions. Here's a brief summary. Don't need to look into details, just to get an idea of what are the contents to these questions. For each of the questions, the score range is either 0 to 1 or something like 0 to 4. And the students can get partial credits on some of the questions. The last column lists the proportion of individuals who receive full score on the question, which is a simple surrogate to how difficult this question is. For the following analysis, we'll try to understand what is the effect of extended time accommodation on student behavior and their outcomes. So there are a few key variables we use for examining this effect. The first is ETA group membership. So out of the LD students, we classify them into three groups, right? Not granted ETA, granted and used, and granted not used. We analyzed the score on each question, which ranges from 0 to whatever the full score on the question is. And we also work with a set of process-derived variables on each item. So for this particular project, instead of working with the raw process data, which is the sequence of actions that are recorded by a computer, we work with some predefined features that are conjectured to be associated with interactivity, which is how much interaction someone has with a particular question. So let's look at the example of a sample sequence, where let's say for a student on a particular item, we observe the following sequence on the top. Enter item indicates they enter this page, the question page. Scratch mode on indicates they turn on scratch work. Draw indicates one stroke in their scratch work. Scratch work mode off means they turn it off. Choose 3 means that they selected the third option in the multiple choice question. And then exit item means that they left for a different page. Enter and exit afterwards at the end might indicate that the student returned back to the question later on, whatever they did, like maybe checking the answer, maybe something else. Right? So based on this raw sequence, we derive a set of features that are conjectured to be related to interactivity. First is number of actions that are performed, right? This is simply the count of how many events are in the sequence. So in this case, it's 8. Second is number of visits. We only included visits that are longer than 3 seconds because maybe the shorter visits are not associated with meaningful cognitive activities. In this case, the student had 2 enter items, meaning that they entered the question twice. So that's 2. We also derived some indicator variables, like whether the person used digital drawing tools. So in this gray part, we see the student did use scratch work on this question. So that's 1. But they didn't use text-to-speech, right? So that's going to be 0. We'll now also look at the total response time in seconds, which is the sum of the time they spend on this item page across visits. For example, they spend like 100-something seconds. One thing to note here is that some of these features, like the total response time and the number of actions, are highly skewed. And in further analysis, we log transform them so the distribution of these features are more symmetric. In order to understand the effect of ETA, we have a few methodological challenges. The first is that the assignment of accommodation is not randomized. And if we're interested in the effect of ETA, there are a few potential confounds. Right? The first potential confound is the differences across the ETA assignments in LD severity or demographics. To address this, we will inspect the demographic variables across these 3 groups to see how different they are. At the same time, another potential confound is the true math skill distribution across these groups, right? Maybe it's possible that those students who receive extra time just did better or did worse in math in general. So we're interested in controlling this confound of their true math skill or knowledge without time pressure. In order to do such controlling, we have to take a leap of faith. And in the current study, we assume that under any of the ETA conditions, whether they receive the extra time or not, there is minimum time pressure on the first 5 test questions on the test. So at the beginning of the test, the student might not be facing a lot of time pressure. And then conditioning on their performance on the first few questions total score, we will try to test for the conditional independence between the ETA condition and their score or interactivity on the later items in the test, which is items 6 to 15. The other methodological challenge we face is that process features for interactivity have highly irregular distributions. And despite that, we try to log transform some of them. They might look more symmetric, but they still look quite irregular. One example are some features that are 1 inflated, for example, number of visits. I came up with the name, which is analogous to like 0 inflated Poisson, where you have a large group of students. Actually, the majority of students, they just visit the question once. So their number of visits is going to be 1. And the rest of the student, they have like a very dispersed count of how many times they revisited the question. So instead of imposing specific distributional assumptions on these features, we adopt a non-parametric test, which is a conditional permutation test for conditional independence, which I'll briefly introduce the intuition later on. So first, let's take a look at the distribution of some of the demographic features in the 3 groups. So the 3 columns are the not used, used, and not granted accommodation groups. All of them are LD students. And here's a summary of their composition into different races, gender groups, as well as their disability severity. There aren't a huge amount of difference. So it's not a very clear-cut difference across the groups. But what we did see is that there is actually more individuals with mild severity in their learning disability in the not granted group, and a smaller proportion with moderate severity. There are some demographic differences as well, which we see that certain race groups, they're more likely to be assigned the accommodation, which can indicate that maybe some parents or some groups of students and their parents are more likely to obtain these IEP or accommodations for their students compared to others. All right. Later on, we will try to further control on the initial performance on the first few questions of the students to test for the effect of ETA. The idea of the permutation test is very similar to differential item functioning analysis in psychometrics, when we're interested in the bias of test questions against certain groups. We're going to treat these students with that ETA, so the not granted group, as the focal group. And we treat the students either with ETA who either used or not used the extra time as the reference group. And then based on the total score of the first 5 questions, we will divide individuals to 4 strata of initial scores. So the first 5 questions, maximum score is 7. We divided individuals to scores more between 0 and 1 across the 5 questions, 2 and 3, 4 and 5, and 6 and 7. And then testing the effect of ETA controlling for performance on the initial items amounted to testing the following null and alternative hypothesis. The null hypothesis H0 is conditioning on the initial performance on the first few questions. No matter what's your group assignment, do you get ETA or not, the expected score on further questions are the same. And the alternative hypothesis is, of course, the opposite of that, where we have a one-sided alternative hypothesis indicating that those students who receive ETA, either those who used it or not used it, are higher in their expected score for interactivity on the later questions. The test statistic we used was actually a simple stratified mean difference, which essentially looks at in each of those strata, what is the average score difference between the students who received the accommodation versus those who didn't. Intuitively, this statistic captures the overall item score or interactivity difference for LD students with or without ETA, with comparable performance on the initial questions. I want to, for those of you unfamiliar with the permutation test, I want to talk a little bit about its intuition. So under the null hypothesis, ETA has no effect. So given the same initial performance, whether you receive ETA doesn't matter, doesn't change your performance or interactivity in the later questions. So if this is the case, it means that the ETA assignment doesn't matter. Right? However, if this is not the case, and if ETA increases indeed score or interactivity on later questions, the SMD statistic we just saw should be sensitive to it and increase. In the case that ETA doesn't matter, then we can randomly shuffle the group membership, which is whether they receive the accommodation or not, within the strata. And that shouldn't change the distribution of the SMD. So here's a toy version of the observed data we have. The permutation test essentially says that controlling for the SI, which is the initial score strata, we're going to randomly shuffle the group membership within each strata. And then we're going to create a total of 1,000 copies of these permuted data, where the group membership, their assignment into whether they have the extended time or not, is going to be randomly shuffled. We're going to compare the observed SMD, which is the one calculated on the original data, to the distribution of the 1,000 permuted ones. And if we observe that the observed one is really far from what we would expect under the null hypothesis, then we'll have a significant, potentially very small p-value, right? And we would reject the null hypothesis and say that ETA does indeed seem to increase the interactivity or score for those students. So here's a summary of the results, first part, which looks at the interactivity of those students who used the extra time. So these are students who were granted time and they also took advantage of it. 3 stars are for p less than 0.001, and you can see that we have a lot of stars over here. The rows are the subsequent questions, 6 to 15, and the columns indicate different interactivity features, ranging from response time, number of actions, visits, and the use of tools like drawing and text-to-speech. Across all of the questions, we see that the students who receive ETA, they actually have more interactions with these questions. They spend more time on all of these questions, perform more actions on each of the questions when they had the extra time. And on most of the questions, they did more visits, and especially on the later questions, they used tools like scratch work more. However, if we look at the students who were granted extra time but didn't use it, meaning that their total response time was still less than 30 minutes, then we saw that they did have some higher response time or number of actions on the few last questions, but not the others. Right? So they didn't actually become more interactive. Something we might care more about is, does having more actions actually resulted in higher scores for these questions, right? That would be useful for understanding whether the ETA is effective. So here are the results. If we look at the score as the outcome, And then even for those students who used the extra time, the expected score was only higher on items 6, 9, 11, and 13. Although across all of the questions, they were more interactive, did more actions, spent more time. And this was also only the case for students who actually used the extra time, not for those individuals who had the time but didn't use it. One thing to consider over here is that we also face a situation of multiple testing. We're testing the hypothesis multiple times. Ideally, we'll want to do some type 1 error control and use a more conservative p-value, which means that some of these results might still face type 1 error inflation problems. So only on 4 questions, there were some differences. Later on, I tried to speculate by looking at why are these 6 questions the ones where we saw granting extra time actually helped comparable learners. So here's my speculation. This plot was for items 6 to 15, some of the summary statistics. The orange bars are the median response time for students who are not granted extra time with non-zero score, which is for those who got some score on the question, what is the median time they spent on the question? The blue line over here is the proportion of individuals who receive full score, which is a surrogate for how difficult or how easy this question is. What we see over here is that items 6 and 9 had the highest correct response rate. And items 11 and 13 had the highest median response time for individuals who receive some credit. With that, here's a look at one of these questions, which is item 13. Very long question. Most questions are not this long. This question is like an intro to stats question, where it says a teacher surveyed 8 students in a class to find out how many pets they each have. And here are some like pie charts and bar graphs that are created based on this. And then I asked the student, based on the circle graph, which of the following sets of data could be the result of the survey? That's not a very difficult question subjectively to me, but it does involve a lot of time if you want to figure out whether each of these are possible. So to come back to our question of how's ETA affecting LD students' interactivity and score, here is a summary of what we found. The first is many students with LD who were granted ETA actually did not use it, and they didn't do better. Simply having the longer time limit and not using it didn't seem to help them do better. And then, given comparable performance on the first 5 questions, those who used the extra time interacted more with later items than those without the extended time. Right? This is indicated by spending more time, having more logged actions, using tools more often, and making more revisits to the same question. And if we assume that the performance on the first 5 questions is an accurate reflection of how students, what students know and can do in 8th grade math, then given the same proficiency, those students who were given and used the ETA could actually benefit from the extra time on certain items. And my speculation, and purely speculative, is that these are the items where they have the skills and knowledge to partially solve if they have sufficient time. But if they didn't have the knowledge, maybe having the extra time doesn't actually help. With that, I want to move on to the second study, which is related to explaining performance gap using a model for latent class mediation analysis. So beyond summary statistics, like we just looked at, we might be also interested in looking at the log data for sequential features. We might be interested in looking at the log data from constructive response or CR questions. A lot of prior studies have separately examined group differences in process patterns or process pattern associated with successful problem solving. However, if we want to make general claims about what process data patterns can explain group differences in final responses, we actually need a unified single model in doing that. So in the following time, I'm going to present some initial empirical results from a latent class mediation analysis, which is called LCMA, on one single constructive response item. We do plan to do it on more of the 15 questions, but for this single item, I think the results are quite interesting, as it turns out that the distribution of misconceptions that result in a wrong response for the general population seems to be different from that of students with learning disabilities. So here's the question. As you can see, most questions on this block are actually quite simple in their formats, right? This question asks you to multiply 4.9 and 1.5. And the process data on this question could include the student's keystroke for the constructor response, so what they type into that box, their tool usage, like scratch work or text-to-speech, as well as their visit and revisit history, indicated by entering and exiting. If we look at the score on this question, we saw that on this item, students with LD had remarkably lower chance of correct response, about 20%, compared to their typically developing peers, about 50%. You run a logistic regression where the outcome Y is the binary score, and the explanatory variable is group membership G, where G is 1 for LD, 0 for TD, and you end up with the following solution, where you can see that the slope in front of G is negative 1.19. It's negative, indicating that those students with group membership of 1, those with LD, are less likely to do this question right. If you calculate the direct effect of G on Y, which is defined as the expected score difference for these two groups, we get negative 0.65. The action sequence data here affords an opportunity for us to explain the achievement gap by uncovering the differences in test-taking process that lead to differences in the final performance between the two groups. So here's the intuition behind LCMA. The action sequence, which records part of the problem-solving process, like specific keystrokes and tool use, can potentially partially explain how a student arrived at an answer that's either right or wrong, the final score. Students with different sequence patterns, like different constructor responses or tool usage, are expected to get different scores sometimes, right? And there might be common sequence patterns that can be revealed by clustering or model-based methods like latent class analysis that summarize these common types of patterns. We know that the LD and TD students differ in their final scores. Our question is, can we try to explain this final score difference by differences in their sequence pattern distribution? For example, maybe LD students are more or less likely to demonstrate specific sequential patterns, like specific constructor responses, and that's why they had a lower chance of correct response. Here's our model summarized in one path diagram. So here the M's, M1 to Mk, denote k-dimensional features extracted from the action sequence data. I'll talk a little bit more about what they are later. G and Y are the group membership and the outcome. You can see that there's a direct effect arrow going from G group membership to Y. But what we also have over here is an indirect effect through omega, which is the latent class for students for their sequential patterns. Different latent classes of students are thought of to be associated with different sequential patterns, which is different distributions in their sequence features, M's. We want to perform variable selection to select the most relevant process features, so that the resulting clusters or latent classes, omegas, from those selected features can maximize the indirect effect. And in this case, we'll try to find overall group differences in scores explained by differences in the distribution of omega, which is do LD and TD students in their percentage of students in each of the latent classes for problem solving. And that might explain how they resulted in different scores. So the M case here are features that are extracted from the raw sequence data using MDS, or multidimensional scaling. This is a technique to convert the variable length original unstructured log data into numerical features of fixed dimensions. Here we use 20 dimensions that are thought of to preserve pairwise sequence dissimilarity. When we look at two sequences by two students on the same question, we consider dissimilarity quantified by the order-based sequence dissimilarity, which considers essentially individual differences in two aspects. So given two sequences by student 1 and 2, are they different in the types of actions they used? And if they use the same action, are they different in the ordering of these common actions? The MDS sequence features, here we extracted 20 dimensions, are unfortunately high dimensional. They're thought of to preserve original sequence information, but they can actually contain information that are irrelevant to the relationship between G and Y. Right? the group membership and the final outcome. For example, some other exams we found that features sometimes serve information on whether someone likes to single click or double click on a question. Well, that's an individual difference, but that's something we might not be very interested in when they're trying to explain like math performance gap. To select the most relevant sequence features, we perform stepwise variable selection to optimize the total indirect effect of omega, latent classes found from the selected features. So the TIE, which stands for total indirect effect, is calculated as follows. You can see that is the expectation of score difference in the two groups, conditioning on the latent classes. The interpretation of this is that this is the expectation of the difference between the score y, or the outcome, in the LD group when the mediator changes from what is expected in the LD group to what is expected in the TD group. So when the omega, which is the latent class distribution, changes from what's in the LD group to the TD group, how much score difference do we expect, or how much increase do we expect, of course. So here are the results. Out of the 20 features, we selected a total of 4 of the MDS features, and 9 latent classes were found based on the 4 selected features. Let's recall that before incorporating the mediators, the direct effect is negative 0.65. However, after incorporating the latent class mediators, the magnitude of the direct effect reduced to something that is still negative, but about negative 0.1. What this indicates is that process features partially explained the relationship between disability group membership and the final score. Didn't completely explain that. Okay, so here are the 4 selected features, MDS features. Not very interpretive, but here's a plot of their histograms. You can see some of them show clear multimodal distributions. What it might indicate is that there are underlying clusters or latent that differ in the distribution of these features. The MDS features themselves are not very easy to interpret. So what we look at subsequently is some of the most representative actions and subsequences in each of the 9 latent classes. I'm going to present 3 of the latent classes that I found that are mildly interesting. Some of the classes are associated with correct response, which is 7.35 in this case. The first is class 3. Some of the most common sequences here included misconceptions that involve things like 6.35, which is one kind of incorrect response. Just to explain a little bit, enter exit, do you know what it is? Receive focus is essentially putting the cursor inside the constructed response text box. And then part 1, followed by this number, is actually the action or the constructed response submitted by the student. So many of the errors in class 3 were associated with incorrect addition of these 2 parts of this multiplication. So you can think of 4.9 times 1.5 as 4.9 times 1 and 4.9 times 0.5, which is 4.9 plus 2.45. Correct answer is 7.35. They might get a 6.35 if they forgot to round up the integer part when they do the addition. Another one is class 4, which is actually my favorite cluster or latent class. So these, a lot of the students in this cluster had mistakes of 8.5 or 4.45, and a small proportion is 29.54. You can see that later on, there are some with revisits, but all of them feature these incorrect responses. It took me a while to figure out how they arrive at this answer. It turns out some students were solving the multiplication by separately multiplying the part left to the decimal and the part right to the decimal. If you multiply the parts left to the decimal point, it's 4 times 1, which gives you 4. If you multiply the parts right to the decimal, it's 9 times 5, which is 45. And if you somehow shovel these 2 numbers together, you either get 4.45 or 4 plus 4.5, which is 8.5. So that was quite cute. The other mistake was 29.4, which my student figured out this was actually summing up 4.9 and 24.5. So this is the case where when they actually try to write down the multiplication, they might have wrong positioned the whole thing and resulted in this answer. So these are misconceptions that are associated with multiplications. And we have another kind of mistakes, which is class 9. And every single person in this cluster had this sequence where they submitted the answer 73.5, which indicates a rounding error where you put the decimal place. We did find that there are differences in LD and TD class distributions, although we need to take a further look to understand what are the details. But what we saw, which was very common, like the 3 clusters we look at, like 3, 4, and 9, actually the proportion of individuals from the TD group was much larger compared to that in the LD group. What that tends to suggest is that for this question, the distribution of LD and TD test takers into different latent classes actually differed. And some of the common errors, like rounding, appeared more common among the typically developing students. To educators, this might suggest that the misconceptions of LD students and how they get a question wrong are different from the common misconceptions in the general population. And maybe for an educator, when they're teaching the LD students and helping them improve on multiplication, and targeting the most common mistakes might be insufficient. I want to briefly mention another study we're looking at that's sponsored by the ARA-NSF Small Research Program. For that project, we're looking at the common item revisit and review patterns in the NAEP for different demographic groups. For example, on this multiple choice question, where you can see there are 4 parts, for each of them they need to tick one of the options. We found that there were 8 clusters in people's revisit patterns. The light colors over here indicates getting a part right, and the dark colors indicate selecting an incorrect answer. And the yellow and the gray are for entering and exiting the question. So here are the sequence distribution plots of these 8 clusters. Essentially, we can see that for different clusters, students were getting different parts wrong or being hesitant and alternating their responses in different parts. So what this indicates, where the x-axis is the action count, is that there are clusters where the students are more hesitant in their actions associated with alternating their responses on certain parts. If we look at the distribution of the LD and TD students in the different clusters, 8 clusters in total, 2 bars are for LD and TD. We can see that, again, the composition seemed quite different across the 2 groups. And specifically, there seem to be certain parts that LD students alternate more on, and those are different from the common misconceptions in the TD group, which is what the general population are more hesitant about. That wraps up my presentation. I would like to thank my collaborators, Dr. Xing Wei from Stanford Research and Digital Promise, Dr. Shuyu Wang from the University of Georgia, and my student Sunbang Kwang, who is currently a PhD student in quantitative psychology at UIEC. And I would like to acknowledge my sponsors, which includes the IES and the AERA-NSF Small Research Grant. And whatever I talk about here does not represent their opinions. Lastly, I want to acknowledge having this nice data set, which is released by the NCES, which includes the response process and the NAEP and the response data from the NAEP 2017 graded math assessment. You might notice that all of the sample sizes here are full numbers as part of the data publication guidelines, where I have to round all the sample sizes to full numbers here, so to the closest 10. Thank you so much, and I welcome any questions.
Very good. And any questions, comments? Yes, please.
Did you analyze anything related to word problem solving? Because I see the example is the calculation.
Related to word problem solving, for students with learning disabilities, I think we didn't. But in another study where we look at students with autism, we did find that questions that are more involved in their social or the verbal context turn out to be more challenging for students with autism.
Thank you.
Yes.
It was really clear and very informative. Thankful to your presentations. I wonder what are the reasons that you select that specific block, that 15 questions in your study 1, and how would you argue that these conclusions that you make in study 1 can be translated to other blocks and questions in the NAEP?
Yes,
Thank you.
thank you so much for the question. That's a great question I didn't touch on here. So NAEP, NCS only released part of the data that they collected from this assessment. And this block, which is the N03 block, is the block where they released their response and process data. Actually, there are two blocks where they release the data. One block is the current one where students weren't allowed to use calculators. Another block with students who were allowed to use calculators. But for all of these students, and the sample I have, they all took this block. So I have a large enough sample size on this, and a small proportion, about 10% of them also took another math block. In terms of generalizability, I think that is a very important question we need to consider when we do process data analysis. A lot of the findings we get here are data-driven and are more speculative, maybe more for the second study compared to the first one. And whether that can generalize and actually be developed into a theory that can generalize to different cases is something that I think requires further studies. So I think process data analysis useful for initial hypothesis forming. So can we discover from the data something that we didn't originally form hypotheses for? And in order to validate these, maybe consider different conditions as well, it probably requires separately collecting additional data, maybe at a smaller scale, then to verify that these hypotheses actually also can be verified elsewhere.
Thank you.
So did we actually release the content of all 15 of the items in the block?
Yes.
So you could potentially do some kind of content analysis to try to interpret what's the meaning of the process results.
Yes.
Okay, that's helpful.
It is. Yeah. It's very, very helpful.
So follow up on this comment. So your block, this block only, I don't know what kind of questions that involve. It's just calculation or there's other types because I only see one example, I guess. So yeah, I would be very interested to see the nature of other tasks to see if
Yes,
just for them can study.
Mhm. Yeah, so
Oh, yeah, yes.
so NAEP has a question tool on their website where you can actually see all of the questions and do them yourself. And they talk a little bit about like what's the correct answer and what this question tries to assess. Here's a very brief summary of the questions. The constructed response was item 3, which is multiplication of 2-digit decimals. There's like an initial interface of like 2 triangles. That was question 8, which is related to rotation of a triangle, like what kind of like counterclockwise, what degree rotation you need to arrive from one to another. There are also some questions that are related to like unit conversion, fractions, looking at the map to work on fraction problems. And the other one we saw was, I think, item 13, which is the like what kind of PET question and translating from the bar graphs to potential data. So very dispersed content coverage.
Yeah.
Yeah.
And as I mentioned, these are the 3 items that really show the group difference, right? Am I correct if I?
So we actually saw group differences on a large number of questions. So on most questions, LD test takers actually did worse. There is actually one exception, which is a question related to, given the diameter of a circle, can you figure out what is called perimeter? Yeah. Yeah, so on that question is a simple formula application, and they actually did better and were less likely to make some common mistakes. But almost on all of the other questions, they showed a difference. I only presented these over here because of time.
Thank you.
Very good. So my impression is after presentation is that statistics will never die, you know. No matter how advanced the AI is, we do need to deal with this data model and by using these basic statistic tools. Very good. So let's thank Susu for her presentation. And now we are going to go to a restaurant, everybody is invited, and will be bar. And we can walk there or we can go there by car. My car can take 5 persons.
Oh, yeah.
Do we have
We have
questions?
questions? Yeah.
Yes.
Oh,
Yeah.
Oh, thank you so much. Yeah, it's nice seeing you, Wenchen. Thank you so much. No questions.
Okay, then you stop
Okay,
recording.
stop recording.
Then we need to figure out, okay, walk there or go there by car. I don't know.
Walk there 20 minutes.